Welcome, everyone. I'm Jesper Gertz, and I'm joined by Hakan Erdomus for this webinar that was co-hosted or is co-hosted by Carnegie Mellon University and the Software Improvement Group. So Hakan, welcome. Let me just quickly introduce you. Hakan, I'm very honored to be joined by you. Hakan is a professor of software engineering at the Carnegie Mellon University, where he teaches software development, software quality, and software economics. He has over 30 years of experience in academia, government, and industry, and is also the former chief editor of the IEEE Software magazine. And for those who don't know what that is, it's a very prestigious peer-reviewed magazine and scientific journal published by the IEEE Computer Society. So thanks again for joining me, Hakan.
Thank you, Jasper, for the introduction. Let me introduce you in return, and thank you for inviting me to this webinar as your co-host. So Jasper is the managing director at SIG, Software Improvement Group, the Americas section. He has quite a bit of expertise in many things, and they include, in particular, related to this talk, technology due diligence, technical debt management, and legacy modernization. He is a true veteran of the software industry with 18 years of experience. And during that time, he has led over 250 assessments. And many of these assessments supported strategic M&A initiatives for Fortune 500 companies. And I'm going to turn it over to you, Jasper, to start the webinar.
Fantastic. Thanks for that intro. So today we're going to talk about software economics, specifically about these topics, on how to quantify technical debt and interest within that context of software economics, how to ensure software quality. This goes into maintainability, security, and scalability of software systems. And we're going to close with some tactics on how to manage risks and optimize ROI based off of these topics that we just went over. And the reason why we do this is that we as SOG, we've seen a lot of M&A work, and of course the industry is booming right now. And once an organization, a private equity firm, or a strategic investor is investing in software, there can be this IT surprise. So this graph visually represents that in a very simplistic way, but it is still quite accurate. So the goal is always a successful integration or a planned exit at the time that we planned for. So that's that greenish line. But an IT surprise can slow that down quite tremendously. So when the engineering team is working on the actual software, trying to understand it after acquisition, it could prolong the successful integration. And that is reduced value. So it's reduced time and it's reduced value. It's significantly more costly. So that's what we're going to discuss today, is how to prevent an IT surprise like this, but also how we can identify technical quality and technical debt in portfolio companies to speed up this successful integration. So I'm aware that not everyone is in software on a day-to-day basis. So let's get to a little bit of those basics and understand what's inside the box. So what you see here is an example of a repository that has source code, right? And this is an example of Bitcoin, and Bitcoin is an open source project, which means that we, the world, can look at all the files and all the code that make up Bitcoin. This includes the Bitcoin protocol, what builds up the network, what validates the block, etc. So this is available on GitHub. You can see the source here on this particular slide. And when we measure this, so when we actually are counting the different files, this is what we see. That's on the right-hand side. We see 29 components, and it's made out of 1,100 or over 1,100 different files and over 500,000 lines of code. And 500,000 lines of code may not be something that is intuitive to everyone. And this is why we put this example here of what is also 500,000 lines, which is 3 times the Tolkien Lord of the Ring and Hobbit books. And source code doesn't read as well as these books, right? It's not a linear story that you're reading. There's very complicated and complex structures within there. that you can build in all kinds of different languages. And in this case, the programming languages used by the developers is C++ and TypeScript. Then we come to the part of the software economics, which is the coder investment time. So this is not necessarily the total time that anyone spent or everyone spent on this particular project. It's a representation of the code that we have right now. So this is these 1151 files. So if one person would need to rebuild all of this code, it would take that one person 64 years. So that is kind of how this calculation works, to give you a little bit of an idea how much this actually is. And you can multiply this by the average cost of a development team and everything that surrounds a development team or that supports a development team to create a solution like this. So that is roughly estimated at 10 million US dollars, which if you look at the value of an actual Bitcoin is of course relatively low, but it represents the software code. And that's what we're going to talk about now. But that doesn't say anything about the quality of this code. It also doesn't say a lot about the technical debt. And this is why I'm going to hand it off to you, Hakan, to dig a little bit into the different aspects of technical debt that we could find.
Sure, Jasper, thank you. So what Jasper is actually emphasizing is that when acquiring new software assets, it is important to consider technical risks and also technical opportunities. Okay? So we're going to focus on the risk side of things, but I'm going to mention a little bit about opportunities as well, because they are sometimes related. Okay? So what are technical risks in the context of software? Technical risks can fall into different categories, and there can be all sorts of things, including lack of external APIs, maybe code duplication in the source code, poor scalability of the system, low test coverage, high defect density. It could be violations of coding standards. It could be lack of modularity, and also things like big ticket items like obsolete architecture. So when we talk about technical risks in software lingo, we usually group them into this concept or condense them into this concept called technical debt. Technical debt is basically kind of what summarizes all of these risks in a succinct way and in a terminology that we can easily use a known metaphor to be able to reason about these issues. So what is technical debt? Technical debt is basically delayed technical work resulting from taking technical shortcuts when we're doing software development. And these technical shortcuts can also be related to non-compliance with best engineering practices. And we take them often not just for ignorance, but to meet short-term priorities. So we kind of want to go faster to be able to, for example, catch a market window. So all of these things basically are categorized under this metaphor called technical debt. So this has some relation to opportunities, because when we're trying to address these risks, we may also inadvertently address some opportunities at the same time. An example would be obsolete architecture is considered a big ticket item technical debt. And when we're trying to address obsolete architecture, we may engage in a modernization initiative. And when we do that, we may enable also some future opportunities. For example, we may allow the system that currently cannot integrate with third-party systems to, in the future, integrate with those systems. And that does not only kind of address the technical problems that we have currently, but also introduces sometimes these future opportunities that may add value. But in this webinar, we're primarily focusing on the risk side of things. So where does this concept come from? Actually, it was introduced way back in the early 1990s by Ward Cunningham, who was a pioneer in the agile software development movement, but it became popular. The terminology became popular only in the last 6-7 years, with now conferences dedicated to it and books focusing on exclusively on managing technical debt and whatnot. I'm going to try to illustrate it also diagrammatically to explain kind of its underlying mechanics. But let's look at the financial metaphor first. So the financial metaphor, debt, as a metaphor for technical issues, technical risks that appear in software products, is actually quite useful. And the analogy to financial debt that technical debt has is not just loose, it's actually quite accurate. Sometimes it holds really almost perfectly. Okay? And we could express it by using these different quotes that are usually common in the context of software development. For example, the idea is that when we neglect engineering best practices, and maybe when we neglect design and architecture, it is just like borrowing money. Okay? When we refactor our software product, our code base, to be able to make it better, more resilient, it's like paying off that principal on the technical debt. When we end up developing slower because we have accumulated too much technical risks, too much of this technical debt, it is like we're paying interest on the loan that we have taken. So all of these kind of analogies actually hold. So because they hold, technical debt is often quantifiable, similar to how we can quantify financial debt. Okay? And maybe kind of an example of that could be the situation where a team saved one person week by cutting some corners. They skipped functional testing, and they did that to be able to meet an impending release deadline. So we know that they will have to eventually do the functional testing because that cannot stay in place. But it has also some kind of side consequences. When we skip functional testing, we may actually incur a productivity hit. Let's say that by doing that, the team is incurring 10% productivity hit while adding new functionality. And why is that? Because when we don't have functional tests in place, then we can't have effective regression testing, and the system may break frequently, and fixing those breakages may be quite costly. So if that is the case, then that percent productivity hit, apart from and if the work that we still need to do, that is worth 40K, that is the principal on the technical debt that we have taken, has these compounding implications. Okay? And the compounding implications is on the whole team. We suppose that the engineering salary is 40K per week. So we skipped 1 week of functional testing. We still have to do that work. That is the principle. We have to pay it back. But we're also in the interim incurring this productivity hit. Okay? If we're incurring a 10% productivity hit, everybody in the team is going 10% slower. So the financial cost of that delayed production is 4K per team member per week. So we're incurring in the meantime 16K per week of cost by just keeping that debt in place, which means that until we pay the principal back, we're going to be incurring that periodic cost inadvertently, and eventually it will accumulate, and it may even start compounding in unexpected ways. So in this case, the consequence is kind of development team facing, but it doesn't need to be always development team facing. It can also be customer facing. For example, if we don't do testing, then we will have defects that escape to production. When we have defects that escape to production, we will have unhappy customers. We may have lost revenues. We may lose new customers that are kind of swayed by the idea that the current customers are not happy with the system. So the consequences can be both kind of team facing, and they can also be customer facing and impact future revenues as well. So how does the dynamic actually play off? And we can represent this by this chart. In this chart, I have the x-axis representing time. So this is basically as time evolves, we have new features added to the system. The system evolves, usually gets bigger over time. And the y-axis represents this concept known in software development called cost of change. Cost of change is basically the cost of, as the system evolves, adding new features and maintaining the system. So traditionally, this cost of change curve is in a system that is organically evolving with no kind of attention to keeping the quality of the system at bay is exponential. So the exponential curve is the red curve. So this is what we call the actual curve because usually in a lot of variety of situations, kind of if we don't do anything about best engineering practices, this curve holds. So this is the curve with no technical debt, with technical debt, and non-compliance, maybe in a rampant way with engineering best practices, and maybe a kind of a substandard architecture and design. So in a situation like this, extending the system, maintaining the system becomes increasingly exponentially more expensive. So when we keep technical debt at bay, we periodically pay it back, and we're consistently using best engineering practices. We're paying attention to architecture and design. We're keeping those kind of reasonably solid as we evolve the system. We have the green curve. So this is the what we call the optimal curve. So these two curves basically cross over at one point. And once they cross over, the difference between them represents the technical debt that we're accumulating by foregoing the best engineering practices, by foregoing paying attention to architecture and design and so on, or foregoing paying attention to software quality. So below that crossover point in the middle, that dot in the middle, we have what we call the strategic region. In the strategic region, we have some choices. Okay? And those choices basically represent a trade-off between paying the technical debt now or taking on technical debt and paying it later. Okay? So we would sometimes be amenable to do that because there are some short-term benefits that we are hoping, and those short-term benefits basically overpower the cost that we can incur by taking on technical debt. So we may try to catch, I don't know, a market window by cutting some corners deliberately. And then once we catch the market window, we can start paying off the debt gradually. Yeah. But this is completely a reasonable strategy, and it's actually done very frequently in software development. So the strategic region is a region where we can maintain or take on technical debt for short-term benefits, but only temporarily. Only temporarily, because eventually we will cross over to that infeasible region after that point in the middle. And in the infeasible region, technical debt will start growing exponentially. And that exponential growth will impact development speed and cost substantially to the point that there will be no choice in terms of paying it back. You'll have to pay back the technical debt, address all of these difficulties. Otherwise, you will make the situation worse and worse. And eventually, it is possible for the whole system to come to a standstill in terms of being able to extend it and maintain it. So this is kind of the theory of how the technical debt dynamic plays out. And Jasper is going to give you some practical examples using kind of two contrasting situations. So I'll turn it over to him.
Thanks. So what we see here are basically two systems, systems A and system B. And they're not exactly the same size, but just for sake of argument, let's assume they are, right? What you see is a bunch of small blocks. We won't go into the nitty-gritty and show you source code and that kind of stuff, but every block here represents a unit of code. That means the smallest executable part of a code base. Right? So there's a lot of those units in these two systems, and the color here represents the complexity of that code, which basically is if-else statements, and nested statements, those type of things. The more complex it is, the harder it is to understand what the code actually does. And the height of the bar means the size of that unit. So a lot of code inside of one unit equals a lot of time to understand what that means, right? So by applying the theory that Hakan just explained, we can arrive to a technical value of these systems. Right? We know the size of this code base, we know the technology it was built in, and we know where the technical debt is, so we can estimate what the value is. And in this example, these are two relatively small systems. It's 2.3 million. So if I were to rebuild this with an average developer, and I only have that one developer, it would take this person a certain amount of time that equals to $2.3 million. Right? So the technical debt can be quantified in a similar way. Because we know there's a lot of complexity and redundancy and all of these other parts of technical debt is in this right-hand system, we can also estimate the repair cost of that, which is also based on a lot of data that we use. But you can see that the left system, although it's much greener, it's not free of technical debt. And that is not a problem at all. Sometimes things are complex and you need to write it in a complex way, or what Hakan just explained, you make a deliberate decision to cut corners in order to speed up development. Still, there is some repair effort that is needed to be invested to make the system better and future-proof. But on the right-hand side, you can see that that is quite a substantial part of the total value of the system. So the debt-to-equity ratio on this right-hand system is 43%, which is quite high. And this is also where you can see that interest coming in. You need more people to do the same amount of work that you were on that system on the left, right? So the cost per year of that system on the right is $400,000 more than the system on the left. So this is how we argue using software economics about what is the technical debt and how can I optimize the investments. And these are just two examples, but I also wanted to go over the benchmark that SIG has been building in the past 24 years that we've been around. And this graph requires a little bit of an explanation. So on the axes here, you can see the size. So this is, again, if one person would rebuild the system, how long would that take? So all the way on the right, you can see 1,000 person years. So these are systems that are built by hundreds of people and contains millions of lines of code. Typically COBOL systems that are dated, they fall in that category, right? Very old legacy systems. However, on the left-hand side, you can see smaller systems, only 5 person years and smaller is there. The y-axis represents code quality. And this is a benchmark measure as we do it here at SIG. So we recalibrate what the market average or the industry average is every year, which basically means if you are or if you're maintaining a system that is of average quality, you can be productive with average speed. That's essentially what it entails. So what I've done is plot all the M&A projects that we've been supporting in the past years on top of this. And then we see an interesting pattern. So of the 573 systems that we've seen, we see that the weighted average quality is 2.7. So that's actually below the industry average. And you may think that's just 2.7 to 0.3 stars. What does it matter? It matters quite a lot. So on the total build value, if you would combine everything, it would be 2 billion. And the total technical debt would be more than $500 million to remediate. So does that mean that these were bad investments? No, not at all. You can still see that a lot of these systems score above the industry average, which means that you can work on this with above average productivity, so make good time, a good speed. But even if it scores below the average, it doesn't mean it's a bad system. The solution can still just do what it needs to do, and customers can be very happy about it. It just means that there's a lot of technical debt that you need to deal with, and that the team that's been building this system has been dealing with in the past years. So if this investment is something that is strategic to you and something that, for instance, needs to integrate into another solution, you may need to remove or remediate some of this technical debt. And that means that you need to indeed make that investment. So quite some interesting data here to look at. I can't reveal much more. Of course, we're under NDA of all of these projects, but we can just look at it through this benchmark lens. So we've just been talking about technical debt in terms of the code quality, but there are many different forms of technical debt. Security is a very important one as well, which is the next topic I wanted to quickly touch on. So within an acquisition, typically what we see is that penetration tests are performed, or the due diligence team is looking at existing penetration test reports, as well as open source scans. Those things are pretty common nowadays. But if you compare a software asset with, for instance, a bank, where in the bank there are these golden bars that represent, for instance, personal identifiable information, a penetration test would only cover the outside of that bank, right? And that's good. It's good. You need to do that. You need to make sure that those walls are secure and that the bars are in tight. But it could be that there's this sewer entrance that you can see underneath that bank that could be a way in. And this is why you also need to look at the code from the inside out. Where in this example, we would say, are the cameras actually on? Is there a person looking at the video feed? How many people do have keys to this vault? Those type of things you can look for. And that's what you see on the right-hand side, where we use our platform SIG to quickly identify these potential issues for an investment, and also quantify, again, using software economics, the costs that are involved in mitigating these problems. And there's a very strong correlation between poor code quality and teams that have taken a lot of shortcuts and security vulnerabilities. And these security vulnerabilities oftentimes need to be remediated fairly quickly. And there's different strategies in order to mitigate this. And this is a form of technical debt. And the mitigation strategies is something that Hakan will now go into a little bit deeper.
Yeah, so let's talk about those mitigation strategies, and we can kind of list them from basically least feasible to most feasible. So we do this by accepting that not all technical debt is bad. So deferring technical debt and paying it back in installments, or even in certain circumstances, not paying it back at all, may be an option. So let's start with that option first, doing nothing ever, and then we accept that it's going to get worse, and we accept that it's going to eventually start destroying value at an accelerating rate. So this is almost always the case when kind of the short-term benefits basically are much lower than the interest alone. You are basically operating in the chart that I've shown you before in the infeasible region. Are there any circumstances where this is an option? Yes, maybe the system is at the end of its kind of life, and it's going to be retired in a few years, and not really much functional extensions are being performed. So when the system is retired, unlike financial debt, technical debt is basically disappears. Okay? So if that is the case, this may be an option. But if the system is in its prime and it has a lot of kind of life ahead of it, it's not going to be retired in a couple of weeks. We're planning a lot of extensions and maintenance activity on it, whatnot. Usually this option is not really feasible. The second option is maybe the system has gone too far in terms of having accumulated technical debt. So we may be considering to replace or rewrite the system from scratch. Perhaps what we can do is, we can salvage some reusable components from the existing system and then, not rewrite those components from scratch. So we may kind of harness some of the salvage cost. But regardless, the rewrite projects that traditionally have been super expensive and risky. And we have some in the literature examples of epic failures, one of the most famous ones being the Netscape rewrite in the early 20s. So when they tried to do that, because Netscape, as one of the pioneering browsers, became really too slow, and it started accumulating too many bugs because it was really organically produced without much attention to many of the modern engineering practices. Netscape people decided to basically rewrite it from scratch, and that was a multi-year effort. And before it became successful, basically Netscape lost its market share, and it died, as a matter of fact. So this is an option, but we have to consider that the option has really high cost and risk and does not always succeed. So the third strategy is deliberately deciding not to do anything for now to be able to reap some short-term benefits. Again, those short-term benefits may be that we're trying to meet an important release deadline. We have a trade show next month, and we have to make our product to the trade show so that we can actually advertise it. We may want to put the product out there with some existing defects so that we can get some beta users in place and whatnot. So there may be many reasons for doing this. And if we have limited resources, then we may have to cut some corners to be able to do that. But if we do that, the idea is to have a plan to pay it back once the urgency disappears, so that we prevent it from becoming unmanageable and we prevent ourselves from moving into this infeasible reason. So possibly in situations like that, the short-term benefits of this strategy is actually greater than the principal plus interest. So it has a net positive effect. So the fourth and fifth strategy are similar. The fourth one is basically having a software development process in which we decide to invest in continuous improvement. So ongoing refactoring to be able to address small and large TD issues is part of our process. If we're doing that, then TD repayment is basically blended into our existing operational expenses. If we're not doing that, maybe we're doing a kind of a more periodic strategy where TD repayment is not continuous, but it is scheduled at different intervals, maybe with dedicated TD reduction iterations. So we pay back technical debt in installments using these iterations in a structured approach. And if we do that, we're basically having a strategy in which TD repayment is kind of organized as a series of capital expense investments to be able to reduce future costs. So in almost all cases, the long-term benefits exceed, in these instances, the principal repaid in installments. And then when we do that, when we reduce the principal, we also kind of reduce the cumulative interest costs as well. So we have kind of a net positive situation. So, what do we do to be able to actually manage technical debt? So, it's kind of obvious that we need a disciplined approach. Okay? And that disciplined approach starts when we acquire the asset. If we acquired a new software asset, we have to know what's inside it. We have to know what the technical risks are in the product that we have just acquired. So we assess and record any existing debt in the beginning, because if we don't know about it, we are basically ripe for these really future, nasty IT surprises. So we run software analysis as part of the due diligence process, collect metrics, assess the amount of technical debt in the product, log the TD items somewhere so that they're visible and they're addressable. For most TD items, it pays off to estimate the fixed efforts. So this is the estimate of the principal. How much will it take us so that we can actually reason about these trade-offs? Shall we pay it back now or shall we pay it back later? For big ticket TD items like serious architectural problems, we also probably need to estimate the interest. What are the compounding future effects of keeping the debt in place? Are we going to get a serious productivity hit? Is it possible that we're creating liability with our customers because we may have these software vulnerabilities that we know exist in the product? And then once we have the asset, then the asset may actually keep evolving. So software will always need to be maintained, even if we don't add new functionality to it in a substantial way. So if we're in a situation like that, we're responsible for maintaining and evolving the asset each time technical debt items are incurred for whatever reason, it is worthwhile to systematically log the TD items so that we can have them visible and the team may have uh, a chance to address them in the future using these deliberate strategies. Then the third thing is to be able to, if we want to be disciplined, set targets and institute a repayment plan. So once we know where we are and we're keeping track of TD, then what is our tolerance level? How much technical debt shall we tolerate before we actually do something about it? Are we going to have a strategy where we pay it back in installments? Are we going to have a software development process where TD repayment or refactoring is basically part of it? It is an ongoing thing. And here, we don't have to be an all or none kind of a situation. All TD is not equal, and some TD items align with the goals of the system, the goals of the investors. Other TD items may actually be irrelevant to those goals, and so we don't have to treat them equally. We can be selective. We're going to address these first. We may drop these other TD items completely. We may have to delay the addressing of these TD items to a future point. And finally, kind of, if we're interested in bottom line implications, and that is usually the case for private equity firms or uh, firms managing assets, software assets in their portfolios, it's important to monetize TD. So look at its financial implications. And with regard to those implications, keep track of what the costs and benefits of addressing the technical debt items are, and then make decisions according to that. So all of this is kind of, it sounds like a big project. How do we do that? The way that we actually address all of these is not manual. Usually, we have ample tool support, and tool support is actually essential. It is needed, and it is widely available at the same time. Software systems are large, millions and millions of code. Now, even trivial systems can have hundreds and thousands of code base. So, without tool support, we really cannot kind of assess the amount of technical debt. We cannot record it manually. We need tools to be able to do it for us. We need tools to be able to track us. We need tools to be able to estimate the amount of effort that goes into paying back the technical debt and so on.
Yeah, and so having that information coming from tools, it always needs to be interpreted by people making plans. And that is the point that you want to make during this webinar, of course, is that there's options. And it's very important to weigh those options. So in this example, where you see a complicated architecture on the left hand side, it could be that the investor here is just interested in this crypto component. So by applying different types of metrics, I'm not going into all the details, but there are certain conclusions that you can draw. For instance, this particular component was built with a data technology. It doesn't mean that we need to update every single component in this system. We can look at this specific component and weigh our options. So that's where risk evaluation comes in, where we can plot what a replatforming, meaning going to a different technology stack, would mean in terms of the total cost in the coming 10 years. That's what you see on the right-hand side. And by applying these type of metrics to the different scenarios, you can compare them. And you can figure out where a return on investment would be if I were to compare it with just keeping it as is and have the team work on this technical debt indefinitely. And this is why that graph goes up exponentially, is that once there is technical debt and teams are still building on this platform, it typically means it's going to get worse and worse and worse and bigger and bigger and bigger at a certain point where you actually need to do something radical. And that's what we propose here. So looking at those metrics and thinking about the investment goals that a private equity investor has allows them to really determine the right ROI for whatever the purpose is of that software asset. And there's some other frameworks that can be helpful here. There's too much to mention and go into, but you can imagine there's process quality frameworks, product quality, architecture, and infrastructure, and so on and so forth. But here you can see the ones that are quite relevant if you're looking at primarily software company, right? So when there's a lot of proprietary software that's being built in the target company, it makes a lot of sense to apply these different frameworks. So just to give an example, you have the ISO 25010, which defines how we can look at product quality. And there are all kinds of sub-aspects that you can see here in the yellow that are relevant, that could be relevant. They are not necessarily relevant for every engagement. So this is kind of where you need to align this with the investment goal. And same goes for architecture quality and process quality. Is the existing engineering team very significant to the solution, right? Do they have specific knowledge that you need to maintain? You need to put them on a retention program because it's very hard to find these type of human resources. Those type of things you can also measure by doing source code analysis. And then indeed, to interpret what these findings means, you can overlay it with all kinds of frameworks, like international frameworks and compliance frameworks. All right, so we're kind of getting to the end of our webinar here. So there are a couple of key takeaways that Hakan and I really wanted to make sure that we hit on. So we can use software economics and this type of reasoning about short and long-term cost for potential investments. And by doing so, you can prevent an IT surprise that we described in the beginning that most likely everyone would recognize as something real. And therefore, thereby reaching those investment goals. So the three questions, there's three things we should be aware of when doing due diligence, acquiring new companies, or when expanding a portfolio of companies, is to perform this type of deep dive due diligence. Understand a software's design, architecture, the state of the quality, the amount of technical debt, security, etc., to really argue about what are the current risks, but also what are the things that I need to do in order to speed up the roadmap development. Secondly, we need a common understanding of what the quality on the dependency of people is and the maturity of the development process. We haven't really talked about this in detail. This was really a webinar about the assets themselves, but people and process, of course, are incredibly important. It's typically people and processes that create or that allow for technical debt to increase. So by understanding how people work and operate, we can mitigate that. And thirdly, we need to develop strategies to address technical debt in a substantial or in a structural way, so we prevent any substantial economic implications. That is something that Hakan clearly addressed just now. So yeah, we have a few minutes left for some Q&A. So let me take a look here. So maybe this is a question for you, Hakan. So what are data requirements for technical debt assessment? So what kind of data do we need in order to do this properly?
It's a technical question. So it depends on the situation and what kind of assessment is being made and what kind of technical debt is it that we're assessing, and what are the trade-offs involved in that. But the kind of data that we need for this may range from easily obtainable information like defect information, including density, severity, fixed effort, fixed timelines, so that we can actually estimate principal and interest costs. Process information that comes from continuous integration, continuous deployment systems like build failures, percent test failing, various static and dynamic analysis measures that are collected, including test coverage, test to production code ratio, size, complexity, code churn, dependency information. If there's periodic refactoring activity, to be able to estimate TD repayment costs, we may be collecting information about when refactoring was performed, what was the effort that was involved, and how did the system improve, before and after refactoring in different dimensions and so on. And so if we have all of this data, we can leverage them with kind of sophisticated or, depending on the case, back of the envelope financial analysis to be able to basically, pit different strategies against each other, perform some scenario analysis, and try to gauge which one appears to be most beneficial in terms of kind of on a net benefit basis.
Mhm. Yeah, I can add to that. With so of course I agree with you, and that's what we do in practice as well during these M&As. But the validation of the data and the data sources is also quite important. In my experience, some of these reports that are available in data rooms, they may be too dated, right? It's there, it's accurate, but it may be dated, and of course things may have changed. But sometimes they're also not accurate, and this is why we always try to validate the findings that we have and reflect on them with the software engineering team to make sure that it's accurate, and they recognize these findings and they recognize the technical debt that is there, because there's an abundance of data, and it's about the accuracy and also the interpretation of the one who's perceiving this. So yeah, that would be my kind of addition to your answer.
Absolutely. And as we know, the problem with data is garbage in, garbage out.
Exactly. Um, yeah, there's of course a question around AI, right? We haven't discussed this, but yeah, the question is, how does AI change this paradigm, right? How does AI impact the way that we should look at technical debt?
Yeah, it's a good question, and I think it also relates to kind of what is the role of tools in support of technical debt management. We have been seeing like increasing integration of AI into all aspects of software development as code assistance, as analytic advice, and so on. And we are also seeing in a lot of software quality analysis tools AI components being integrated to be able to make kind of best practice recommendations and whatnot. Yeah. So definitely, so like in any other field, AI is going to have an impact and probably will be a kind of an integral component of TD management, because the tools will basically kind of provide advice, at least
Yeah.
partially uh, based on models that are trained by AI systems. But there is a caveat, and that caveat is that usually AI systems are trained using existing data, historical data that comes from software practice. And implicitly, that data represents average practice. And when you represent average practice and then give recommendations based on an average practice, you're basically supporting reversion to the mean. So everybody is advised to basically kind of stay around the average. And then those people follow that advice, they produce more data that train kind of the future systems, and then it kind of feeds itself. And
Yeah.
then everybody is basically converging to this average practice rather than maybe novel practice or best practice. So the caveat is that if the data is biased in this way, then you should not expect improvement in the advancement of the current practice into a better practice. We will just stay exactly where we are
Until there are better models trained on
until there
high
are better models.
quality
And
code. But then
but
I agree with you. I agree in a large extent to what you're saying, because it will normalize. It's our perspective is, if you're, and we are using this benchmark approach for a reason, if everyone in the world is going to use Gen AI and code assistants, probably productivity will go up. Maybe code quality will even go up. But if everyone is doing that, it just normalizes the output. So we're going to have more volume that we need to manage. And yes, we can use AI to assist us in helping us do that. But that doesn't mean that there's no responsibility anymore for the engineers or the people that actually need to, or that are relying and building on these systems. So it's something that is going to be here and it's going to stay here. I'm pretty sure about that. But it will normalize. So even until the moment that we are no longer in control as human beings, I guess that holds up. Programming will change in the way that we do it, but we still need critical thinking. We still need to know what we want and how we want it. And yeah, just the tools that we are using are going to change. And we've seen this. We've seen this in the past, how many years? Many years that we've been.
Yeah, that's correct. Also, I think kind of what's going to happen eventually is that currently, code assistants, AI-based code assistants don't rely on success measures. So they give you advice that represents the majority. But if we have success measures kind of attached to that advice, that advice is optimized, to increase a metric. I don't know. And
Yeah.
that metric has meaningful implications, then we can move towards kind of advice that actually increases software quality rather than make software quality stay at the average level that the industry practices. Right now, that is not there, and provided that data models evolve to involve these success measures and try to optimize the advice according to these success measures, then we have a chance that the practices will, the recommendations will push the industry to actually improve their best practices.
Yep. Yeah. It's an exciting time, though. And it's an exciting topic that I'm sure we can talk about much more. But we're kind of at time, a little bit over time, actually. So I'd like to thank you a lot, Prakan, for co-hosting this with me. I think it was an interesting topic. Sure, more to say about it. And thanks everyone for joining, listening in, and of course, drop a comment on LinkedIn, and we can address that, of course, as well. So with that, thanks a lot.
It was a pleasure. Thank you.